Alright, so in this video we're going to talk about the events that occurred from the Big Bang all the way out to 380,000 years. And that turns out to be a significant date for reasons that we'll get to. So we start kind of where we left off for the last quiz. So this is Hubble. Not only did he discover several things, he's also the scientist most photographed nonchalantly smoking his pipe while making discoveries. The two things that Hubble discovered that are important to us in this course is the first one is he was the first person to find variable stars in another galaxy. And this was important because variable stars are a really great tool for measuring distance. We always know their brightness based on how long it takes them to go bright to dim to bright to dim. And when he found one of those in a distant galaxy, he was able to measure the distance to that galaxy. And this picture is the Andromeda Galaxy. This is a slide of the first variable star he found there, and it turns out to be 2.5 million light years away. The second thing he did was he looked at the spectrum of light emitted by the stars in these galaxies. And in particular, in this example, the lines created by the element of hydrogen. Hydrogen makes the same lines when the atoms are excited. So we can see it down there at the very bottom. It says laboratory reference. So that's the lines that we see emitted by hydrogen, the spectrum lines. What Hubble observed is these galaxies that he looked at, and as he measured the distance to more and more distant galaxies, he saw that the lines were shifted toward the red end of the spectrum to a greater degree, which says that A, they're moving away from us, and B, the farther ones are moving away from us faster. So those are the two things that Hubble did. Then there's an arrow that shows the shift in those spectral lines. So you can imagine it as something like this. So the galaxies that Hubble observed were not flying off into space. They weren't expanding out into space. Space is expanding. So the space between the galaxies is getting bigger, and as space expands, those waves stretch out. They become shifted to lower wavelengths, which is the red end of the spectrum. So this balloon analogy is kind of a nice one in terms of understanding what's going on here. So in each one of these pictures, it's the same galaxies. They're just getting more and more and more spread out from each other. So the next step, we talked about this Belgian priest named Lemaitre, who took Hubble's information, his discoveries, and ran the clock backwards. So he said, okay, well, if everything's heading out, at some point in the past, everything was closer and closer and closer together, which leads to the idea that everything started at this one point, the singularity they have labeled in this picture. So that's where we're going to start our story with today. What would have happened in a universe that started at a single point? And when we talk about this in science, everything is supposed to be based on observable, measurable evidence. So we'll talk about what we can measure. The problem with the Big Bang is at a certain point, or I should say up to a certain point after the Big Bang, we couldn't observe anything. The light wasn't traveling anywhere. So most of our story today is going to be based on sort of a model of the Big Bang. So based on what we see in the universe and based on what we understand about the universe, what would have happened in a universe that started at a single point. So if we imagine the universe, so this is kind of what Lemaitre did. If we head backwards, the universe gets smaller and smaller and smaller and smaller. So you can see that tiny little point there in the middle of the page. The universe would have been even smaller than that, like the size of an atom. And the first thing but people had a lot of trouble with this. People were very skeptical of this initially. And one of the first things people tried to wrap their minds around is, well, how can all of this stuff that is the universe, all the matter, all the planets and people and stars and everything that is the universe, occupy a single point smaller than an atom? So that's kind of the first hurdle we have to overcome to understand this. And the way we overcome that hurdle is that in the 1940s, human beings figured out how to do this. Nuclear weapons, right? And nuclear weapons, among other things, nuclear energy and things like that, are based on the equation E equals mc squared. By the way, this is kind of a good time to stop and say that as we're telling the story, we're sort of painting a picture in broad strokes here. So there are details that we'll kind of gloss over, and there's some things that we're not going to worry about right now. If you want to know more about those, there are resources we have that we can look into. But But for now, it's enough to kind of look at the big picture. So this equation, discovered by Einstein, the E is energy, m is mass, and c is the speed of light. What this equation tells us is that mass, matter, is really just a form of energy. We can convert between the two of them, and if you convert mass into energy, just a little bit of mass releases an extremely large amount of energy. So this, in a nuclear explosion, is different than a conventional bomb, right? A regular bomb or regular explosion uses a chemical reaction that releases energy. In this case, it's the conversion of mass into energy that releases all of this energy in the explosion. How this is helpful in terms of understanding the Big Bang is that this single point doesn't have to have all the mass, all the stuff that makes up the universe. It can just contain the energy. So it's highly energetic, incredibly dense, tightly packed, but we don't have to have all the mass there quite yet. So as this expands, we're going to look at kind of a few significant events in the expansion of the universe. And the first one we're going to stop at is about a billionth of a billionth of a billionth of a second after the Big Bang. So the universe is softball sized. At this point, the four fundamental forces have formed or are forming, and those are gravity. We're all familiar with gravity. It's the attractive force between masses. Electromagnetic, and that's positive and negative charges attracting and repelling. The strong nuclear force is one you may not know too much about. It turns out that's the force that's responsible for holding the nucleus of atoms together. So in an atom, really the nucleus of an atom is made up of protons, and protons all have positive charges, and positive charges want to repel each other. But it turns out if you get them close enough, there's a strong nuclear force that takes over that can hold those things together. So that strong nuclear force is really important in terms of atomic structure. And then the weak nuclear force is that's the force that's involved in radioactive decay and things like that. We're not too worried about that. So that kind of doesn't play into our story very much. So we'll kind of set that one off to the side. So we have these forces. And then a billionth of a billionth, sometime later, a billionth of a second after the Big Bang, the universe has expanded even more. And in that short amount of time, it's expanded out to 10 to the 25th, so 10 with 25 zeros after it meters across. So this tremendous amount of energy that's stored in that softball-sized universe pushes the universe out and expands to something very, very large. And at this point is when electrons and protons and neutrons start to form from quarks. Quarks form initially, and then we have these subatomic particles that we're a little more familiar with start to form. These will eventually go on to make atoms, but the energy is so high in the universe that they're moving too fast. There's no way that they can settle down so that positive and negative charge between protons and electrons can attract each other and create atoms. So the universe is just a mess of energy and electrons and protons and neutrons. It's actually so dense that if you had a piece of the universe the size of a stone, it would weigh as much as 25 elephants. So it's extremely dense, but it's at least something that we can kind of start to wrap our minds around, numbers that we can sort of start to understand. Not only is it very dense, it's also extremely hot, and it's a state of matter that we call plasma. So I know we're familiar with solids, these atoms and their crystal structures, and then liquids where things heat up and the atoms can move around each other, and then gas where they're more dissociated. A plasma is a form of matter where the energy is so high that the protons and electrons aren't even associated with each other. So they're moving around completely independent of each other. And also at this time, the density is so high that the universe is opaque, which is to say that no light can travel through it. Transparent is the opposite of opaque. So the universe is so dense that light can't travel across the universe. It's just energy that's contained in the universe. Kind of an analogy to this is the center of the sun. The center of the sun is under such tremendous pressure that enough heat is generated to create a plasma. So it's extremely dense, extremely hot. So in a sense, the entire universe was like the core of a star. There's no outside, there's no space really to move around in. It's all really dense, hot, pure energy and protons and neutrons and electrons flying around. As things expand, though, they cool. And as things cool off, things slow down, and eventually things at about 380,000 years in, things got cool enough for the protons and electrons to associate with each other and form atoms. So the positive of a proton and the negative electron, they're attracted to each other, and they can create hydrogen atoms, and there's enough pressure to push some protons together, and they can create helium atoms. So the universe at this point is about 75% hydrogen, 25% helium, and a few other little bits of other atoms, other elements are there too. Now this is a very significant event in the universe because once things condense into atoms, we have space. We have a lot more space. Things have cooled off, but there's also more room for the light to move around in. And scientists theorized that when this happened, that all this light was trapped inside the universe, that when things condensed into atoms, all of this light would suddenly be free to move about the universe. It would be released, and the entire universe would flash with all of the light that had been stored inside this plasma state for 300-something thousand years. And in this point of the story, so people thought, well, all this light would be released from the universe. We're going to take a little tangent here for a second and talk about microwaves. The picture here on the left is a cell phone tower. The picture on the right is a microwave tower. Cell phones use microwaves. It's a form of light, just like visible light is. It just happens to be a light that we can't see. In the same way that you can produce sounds that are too high or too low of a frequency for human ears to hear, this is a light with a wavelength so big, so it's a frequency so low that our eyes can't detect it. But we can build things to detect it. And it turns out that if you want to send microwave signals, your cell phone actually uses microwaves. It's actually just something like a flashlight in the microwave region of the electromagnetic spectrum. If you could see microwaves, whenever you got a phone call, your phone would emit light. It would look like a flashlight. So in the 60s, people were trying to develop this method that we now use for communication, and AT&T was working on microwave communication, sending signals across the air via microwaves. But whenever they tried this, they always got this background noise. And so they had these two scientists. Their names are Penzias and Wilson. They're Arno Penzias and Robert Wilson. And their job was to figure out where's this background hiss coming from and how can we get rid of it so that we have a clearer signal. So this is a picture of them on their antenna, and it's kind of a funny looking antenna, but it's an antenna designed to pick up microwaves. And basically, as they pointed it to different directions trying to isolate the source of this hiss, they found that there was this uniform background microwave noise. Not noise, I shouldn't say noise because it makes it sound like you could hear, but background radiation, background light that was coming from every direction across the sky. And there are some known sources. There's stars, and the Milky Way emits microwaves, but when they subtracted those out, there's still this background hiss of microwave light. So they were trying to figure out what it was, and in their attempts to figure out what it was, they contacted a group of scientists at Princeton, and the scientists at Princeton turned out were studying the early Big Bang and were working on predictions of what this light that was emitted, this flash of light that would be emitted when all the atoms formed. Their prediction matched exactly what these guys were hearing. So they actually got the Nobel Prize for discovering this background radiation that people thought would exist. So just so we're clear about what's going on here, think about this. So let's say the universe was a flat square. So I've moved it back a little bit so that it looks a little depth to it. But so in this early universe, so this is billions of years ago, there's I shouldn't say a star, but a light source on one side of the universe, which is that orange bubble, and then the Earth is going to show up eventually. We're not here yet in this early universe, but the Earth will be there where that green dot is. So as the universe first emits this light, let's assume that that light is pretty high energy. It's visible light, it's ultraviolet light. So this is the kind of light that's being emitted from that early universe. As the universe expands, all space, all things expand, including that light wave. So as the universe expands, that light wave expands. So the wavelength gets bigger, and you can see we've shifted to a longer wavelength, which is farther to the left in our electromagnetic spectrum. So the light's not all visible in ultraviolet now. Maybe it's red and infrared. And as the universe continues to expand, that wave gets bigger, and you can say I've changed it to a redder and redder color because it's red shifting. It's getting bigger and bigger and bigger. And then by the time it arrives to Earth, now we're there, 13 point something billion years later, it's shifted to the microwave end of the spectrum. So what that means is that light that star emitted way back here, it was visible light. It was the first light that left the early universe, is arriving to us right now, but it's not light we can see. It's microwave radiation, which is exactly like light. It is light. We just can't see this kind of light. If you could see this light, if our eyes were eyes that could see microwaves, the entire sky would be glowing right now with this light that was released from the early universe. So, what does it look like? So people thought, well, we can see this light from the early universe. We can actually see what the early universe looked like. The way people decided to study it. Oops, I forgot the slide was in here. Yeah. Okay, so people wondered, what would this light look like? And if we can see it, we should be able to see the early universe. And what information could this light give us? Well, it turns out that light always carries with it some information about the thing that made that light. And one of the things it can tell us is actually the object's temperature. So this graph might not be super clear, but what it's supposed to show is that, if you can see where it says 3,000 Kelvin or 4,000 Kelvin or 5,000 Kelvin, as things heat up, the wavelength of light they emit gets smaller and smaller and smaller. If you think about it, an electric stove, when you first turn it on, those coils start to glow red, and then red, orange, and then they get brighter. So the hotter something is, the bluer the light that it emits is going to be. Now, it'll never glow blue. It'll glow white hot because it'll emit every color in the visible spectrum. But what people knew is that the temperature of something affects the wavelength of light that it produces. So if we could look at this microwave radiation and we can measure its wavelength, we would know some things about the early universe. So in order to do that, put together this satellite called COBE. It's a C-O-B-E. And it's basically our microwave eye. So humans can't see microwaves. This thing is scanning the sky out in space, picking up this microwave radiation that's coming from every direction. And the map that it made looked like this. And I know it doesn't look like much, but this is actually a really impressive picture. This is a map of the entire sky of the microwave radiation that's arriving at Earth from the very distant past universe. It's color-coded. The blue areas are hotter, and the pinkish red areas are cooler. And what this said to people is there was some organization to the early universe, that it wasn't uniformly distributed. There's some structure to the early universe. It wasn't uniformly distributed, that there were hot areas and cool areas. And the hot areas would have been where there's more matter, and the cool areas where there's less. So this gives us an idea of the very first structure to the universe. And people really were impressed by this map, so impressed that they built a second satellite called the WMAP. And this one gave us even finer resolution picture of the cosmic microwave background. And so this picture, and again, it doesn't look like much maybe, but what this picture is a map of the very first light released when the very first atoms formed 380,000 years after the Big Bang. And when we look at this, these blue areas indicate areas where there's more energy, more mass collected in those areas, and the redder areas are where there's less. And so what we understand, what we believe is that in those places, that's where more mass is going to be. There's going to be more gravity. So eventually those blue spots will be the places where the first stars form and where the first galaxies form, that ultimately leads to the structure we see in the universe today. One interesting way to think about this is if we go back to this slide here. And we've sort of looked at this slide from the Earth perspective, that all of this light is showing up at the Earth. Well, this works the other way too. So in the early universe, there was light leaving the green dot too, headed toward the orange dot. And so that light got redshifted and redshifted and redshifted. And so if we ran that the other way and that gray line shows up at the orange dot, maybe there's some alien civilization that sent up their own microwave probe and they've mapped out the sky from their vantage point. They wouldn't see the exact same thing as us. They're seeing the light that arrived from our part of the universe that left our part of the universe and arrived there. But in their picture, in one of the blue areas in their picture where there's more structure, that's where our galaxy is going to be, and that's where our sun's going to be. So they're looking at a picture of what will ultimately become the Earth from their viewpoint. So that kind of is the big story, sort of how the Big Bang started. And again, this last bit, that's the only observational evidence we have. Without that, it's all, I mean, it's solid science. It's based on discoveries made in super colliders where we can crash subatomic particles together and create sort of the same energetic conditions that occurred in the Big Bang, but we can't observe it directly. But that tells the story, and that kind of sets us up for the very next thing that's going to happen, and that's the formation of stars.